eval workshop, Embodied Vision, Action, and Language, and this is our invited speaker panel. I want to briefly motivate what some of the core ideas of eval were, and then I'll sort of ask some initial questions to get us started. So what eval is trying to do is bring the idea of combining language and vision, which has gained a lot of traction in the last 2-3 years, especially with work by one of our co-organizers, Peter Anderson, on sort of vision language navigation work, especially on taking visual inputs and language instructions and having them correspond to agents actually taking action in the world. And bringing this all the way into ECCV, part of our motivation is that people in the vision community have actually been looking at problems like this for some time. Kristen Grauman is one of our speakers, has been working on egocentric perception since at least 2014 or so when I started at UT. Gino has been working on robot navigation in the real world, conditioned on language, as has Nick Roy. And then Jason Baldridge has gotten involved in these VLN style activities recently, with Chelsea bringing in things from using artificial or templated language to do real sort of large scale manipulation and simulation environments conditioned on language. And so in all these cases, we have people bringing together not just language and vision, but also action taking, and particularly action taking with some kind of agent in mind, often an actual robot platform. And it turns out this is just like extremely hard. And I know all the PIs here appreciate the difficulty of that problem. So I think having watched all the talks, there's a lot of potential for overlap in sort of philosophy of which are the hard problems here. But I think for me, at least, the most interesting thing to hear from you guys would be among language as input to condition agent behavior, controlling an agent to actually get it to do something in the environment, and processing visual input and sort of tying it to both language and actions. What's actually the challenge here? What's the bottleneck? Is it language? Is it vision? Or is it robotics from your perspective? And I'm going to turn my video off and mute myself as you guys answer, just because I'm not as interesting, but I'll come back with the next question in a bit. And anybody can start. If you don't, then I'll pick somebody.
Well, I think there's a variety of reasons why it's hard. I think one is that even with the increasing proliferation of data sets that are driving progress, and there really has been a surprising and satisfying growth number of data sets, I think data that captures how we would want a real embodied intelligence, or data that captures the circumstances and the environments and the tasks that we would want from a real embodied intelligence like a robot, still seems to be hard to get at. And I think that's it's just hard to gather data with robots a lot of the time, especially robots that are moving around. And then it's also I think the best techniques right now are still quite data hungry, and so you have the techniques driving wanting a lot of data, while at the same time it being hard in this particular domain to get data. So I think that is probably one of the tall poles, but some of the other panelists may have other thoughts as well.
Yeah, just to add to that in a similar spirit, it seems to me like there's a lot of motion on the kind of static environments that can be really, photorealistic and great for navigation-based tasks on their own. But harder, of course, to model is like the simulator for things that are interactive, and so that you can actually have the agent changing the environment, and ideally in ways that look like, coming from the vision perspective, that look like how it's going to look when they do it in the real world. And certainly for very obvious reasons, that's hard to do as well. So I don't know, day to day when we work in this space, that's just a practical challenge we're up against. If we want to be able to explore and train in simulation, just to not only understand what we're dealing with, but eventually approach some kind of sim to real transfer, then the interaction-based things like an agent opening a drawer, but not to mention an agent like trying to tie shoes or something like this, is just so much harder to model realistically. So I think that's like a practical challenge in the research space right now. The other one I would briefly mention is how do you train for these things? And I think there's been a lot of interesting work, trying to be creative in this regard. How do you, move from traditional supervised, cut and dry, X goes to Y type of learning to this more open form of learning where generalization means not just new instances, but new tasks, that you haven't seen before and in environments you haven't seen before. So that's a very fundamental challenge, but it seems to permeate a lot of the work explored in this workshop.
Yeah, and to maybe follow on what Kristen said about the dynamics of the environment, I think there are dynamics of language that are very hard to capture at scale in these sort of simulated environments, right? We can do sort of synthetic language generation, but then that's not real human language. And so we probably need to look to some sort of setting where we can actually have people embedded in kind of an environment where agents can be trying to move around, talk to them, work with them, interact via language. That's also very hard to scale. It was pretty cool to see just the other day. I think Facebook was talking about or released a paper where they actually had people playing games with agents that involve language, and that's exactly the right kind of direction. I don't know exactly what the dynamics of the environment itself were. It looked like it was kind of a text-based thing, but I think mixing that kind of idea in with these sort of more 3D simulations, photorealistic environments is going to be important.
Yeah, I agree with everything that's been said. I think that even the problem statement and what supervision should look like isn't clear cut. And in many ways, I think that's a good thing. It should open up kind of more interesting techniques coming forward. In principle, I think that the language aspect of this problem should make supervising these systems easier, because it's easier for average people to provide language information to a robot. But at the same time, it does seem like there are challenges kind of bridging the gap between this kind of representation of the world in language and actually the representation of the world that the robot sees. And so I think that there are a large number of challenges. I think that maybe to me, the key challenge that comes up is thinking about how do we supervise this learning problem in a way that's scalable, in a way that we could ideally collect data even in the real world and collect supervision on top of real data, such that we could learn from that real data without having to require a significant amount of online data collection. Maybe if you can instead leverage offline data, that might be more scalable, and without having to require a human in the loop every step of the way. If instead you can kind of require a single offline data set to be labeled offline, then that might make it more scalable to actually deploy these approaches in the real world.
Yeah, I think I also agree with what everyone has said. And the difficulty to me, the robotics is such an applied field, so the problem becomes much more complex. So I think one good thing that happened recently is having a much simplified problem that combines language and vision navigation together. So the vision language navigation, they have a data set so that doesn't fully represent the real problem, but it captures enough so that we can work on it. So I think if there are more efforts to create a simplified problem that combines these different modalities, I think that would be great.
So that's interesting, Jean. I was actually going to observe sort of the opposite of that. Is I wonder if some of the data sets are actually too simplified. So you and I, we work with real robots, and so we know how hard that is. I think a lot of the efforts to turn sort of vision-based navigation into essentially question answering, I think might actually abstract away a lot of things that actually make the problem hard as well. So while I think we all agree there's a lot of data sets out there, and I think, Jean, you're right, like some of them still are probably still too hard. It's not a lot of data sets that actually involve real robots, and there's lots of ways in which having a real physical robot actually have to do the navigation as opposed to simply go from picture to picture to picture. Introduces, forces you to deal with a lot of the hard problems of, data set bias, also the actual navigation piece. It forces you to deal with when the task is underspecified with respect to the robot. These are things that I think are not well captured by the existing data sets.
So I absolutely agree with you, Nick. So the data sets are somewhat overly simplified, but it still provides some way to evaluate approaches and compare performances. So that didn't exist before. So everyone does a robotic experiments. So it was hard to make progress because it was hard to evaluate. So having something that's measurable, I think it is like a progress.
Yeah, so I totally agree with that, but that is, I mean, that is sort of the heart of robotics, is that evaluating real robot systems is just really, really hard. And so I think the evaluation data sets do represent progress, but we've got to make sure that we still are evaluating. We need some way to actually get to the problem we actually care about.
So quite a lot of people have been talking about data sets and, you know, I guess the flourishing development of them, but also the need for more data. One thing that we've observed in the vision side and the language side is that we now have these very good general purpose representations of language, like BERT or vision, you know, like whatever style of resonant you like, that transfer across tasks. And you know, this is, I guess, one of the things that's like really pushing benchmarks forward. And so I wonder if I can kick off a discussion about a general purpose action representation. And, you know, if it would even be possible to have such an action representation that would transfer across tasks and robot platforms, and what would be the massive amount of data that, you know, we might use to train such a thing.
So in terms of something that transfers across robots, we've actually been trying to go in this direction a bit, where we recently collected a data set that we somewhat shamelessly called RoboNet, that has data from 7 different robot platforms across 4 different institutions, with the goal of understanding, can we start sharing data across institutions rather than in robotics always collecting data in the context of a single robot and a single environment and so forth in that one lab. And we have seen some kind of promising signs of life there with regard to being able to leverage data from other robots in a way that allows you to transfer to a new robot and fine-tune to a new robot, for example. So I think that there is some signal that we should be able to actually share data across different institutions in the same way that computer vision data sets are shared across institutions, and in the same way that natural language data sets are shared across institutions. In the robotic manipulation setting, I think that how you do that transfer is still, of course, an open question. And I think that the answer may also differ between manipulation and navigation. In navigation, it may actually be much easier to do this sort of transfer because you don't necessarily have to actually even look at the robot. Whereas in manipulation, a critical part is looking at your arm and using kind of hand-eye coordination to interact with the world. And there you see more visual discrepancies between different platforms.
That sounds really cool, Chelsea. Is that like, you have a link on your website about that?
Yeah, there's a link on my website. And it was a paper that was at Coral in 2019 in November.
Okay. So the one thing that so I think your point about navigation being a lot easier than manipulation is also a really good one. One of the things that makes manipulation really hard, and I think also is going to make learning a representation in the way that the natural language and computer vision have done it, is that manipulation is fundamentally unsmooth in almost every conceivable way. You know, the dimensionality of the configuration space changes as you pick things up and put things down. As you travel in and out of contact, you have massive discontinuities, total loss of gradient. And so traditional techniques for learning learning representations and learning embeddings, et cetera, basically have to have a hand-coded structure imposed from above. And that is often the thing that breaks and is often highly tuned to the task in the application. So I think the problem is that the learning techniques for learning general representations are really, really poorly aligned to the actual nature of the manipulation problem, and that makes it hard.
So for me, one of the things that would be really exciting about having kind of a really solid, robust, common set of like way of representing actions, and also low-level representations for space, is the connection to language. One of the things I discussed in my talk was this idea that comes from decades ago, that in order to understand abstract language, what we possibly do is we run mental simulations of low-level actions that are concrete actions, and then we lift that into an abstract space. So, I grasp a spoon or I grasp an idea, and the idea is that I have some sort of low-level way of simulating in my mind what grasping a spoon is like when somebody says, grasp the spoon. And that I use actually very similar mechanisms when I'm trying to grasp an idea. Similarly, we use metaphors all the time to talk about things like, companies, reaching profitability, or countries falling, the interest rates falling, these sorts of things. So we're constantly using spatial metaphors and these sorts of things, and having a really robust sort of action and physical representation space is possibly the substrate that we need to get at abstract language, which honestly is kind of what motivates me in the long run. And then I also think there's kind of potential bridges in terms of conceptual spaces that could be the link between language and these low-level kind of representations vis-a-vis Peter Yardenfor's conceptual spaces and other kinds of ideas like that. So I think getting the action space right is probably right for doing practical things with robots, and also potentially for long-term theoretical questions in like meaning and linguistics.
One thing I also wanted to bring up was the language integration. Like, it's not like always the case, but we can discuss language and action integration in a more abstract space, something like using a very simple simulator or synthesized environment. But the perception and action integration is more low level. So if you look at the biological systems, like animals that do not use language, it still has very good mobility, and they do very good coordination with their perception. But if we include this high-level reasoning and planning capability for like understanding the task-level description, that is more kind of higher level intelligence. So maybe the language action is done in a more global or high level planning, and then the perception action is done at the low level. So, yeah.
Yeah, I'll add one more thing from the computer vision side. So if I think about being able to have some kind of action primitives that are modular, reusable, from task to task, or at least environment to environment, an attractive line of thinking is to model, this is in the video, even in the video sense, but like modeling what we see for actions by ourselves, being the agent, or others, not in terms of exactly what it looks like, but the effects of the actions. So, you can think of an action as a transformation where things were this way, now they became this way. And that alone is very important on the computer vision side, potentially, because now you can think of it as translating from what the agent does to how people do it, to how the agent with this hand versus the agent with that hand would do it. If we can model, the precondition, the postcondition as the visual thing we care about, as opposed to exactly how it was accomplished and how that looked visually. And so kind of making that difference is a potential path towards having such action primitives, I think, specifically coming from the visual perspective of what are things we need to pay attention to, or what should the models be locking onto when they try to encapsulate what a reusable action is or what it looks like.
Thanks, guys. I'd like to maybe ask what sounds like a follow-up to Kristen, but is really an opportunity for more discussion, I think. So, Kristen, at least in the talk that you submitted for this workshop, you discuss a lot about this notion of treating action as sort of precondition and postcondition, and how doing something in the world changes it, right? From finding these sort of like grass hotspots for manipulation to the exploration of the AI2 Thor environment for figuring out what's toggleable, what's placeable, what can be picked up. And I wonder, from your perspective, going down to this low-level action abstraction, is there room for language? Is it like time to even try to condition this kind of behavior on language yet? Or do you feel like we still have a lot of work to do on the modeling side for understanding how to move around and interact in the world in the first place?
Yeah, Jesse, just to understand better your question, so do you mean is there room for language to help us learn visual affordances? Like if, in the sense of, yeah, maybe an example of what you have in mind to make sure I understand.
Yeah, sure. So using language as an additional signal is certainly one aspect. I think that's the one, say, like Chelsea is most amenable to. But I'm thinking more using language as a way to direct the agent's behavior, like specifying a goal in natural language or an instruction in natural language and trying to have the agent infer a sequence of actions that needs to be taken to accomplish that in the environment. Like if it doesn't understand how the environment works in the first place, obviously it's not going to succeed there.
Yeah, I mean, we have, preliminary results for this that I briefly touched on in the talk where like we would take language-based instructions for a handful of tasks, calling them downstream tasks, and then say, if we just learned policies to achieve these tasks without these visual affordances, how fast or how accurately can we learn? And the affordances were helpful. I mean, one thing when I think of language and affordances, one thing that I'm aware of, but we haven't, I don't think, dealt with yet carefully is that, we're adopting, just as we adopt from language, even these taxonomies of what objects are worth mentioning, what actions are worth mentioning. Same thing, of course, for the affordances, right? And there's like this delicate, interesting interplay between like what we would describe as people, as researchers, building these models that get them into this taxonomy and these shades of meaning they have. I mean, Jason a few minutes ago gave good examples of like, these words can have different meanings or they can have abstract and concrete ones. Same goes for the fact that we take a space of verbs, say toggleable, placeable, reachable, all these things for affordances that decide exactly how we're carving the space and how the space would be viewed by the agent. And that's clearly coming from language for no reason. If for no other reason, then we need these vocabularies to start, having discrete buckets for these models to build, in our case, segmentation maps that say where you think you could do these actions. But that seems like another layer we could question or revisit in terms of, I don't know, like how the sharing should take place among the different meanings of these words. So, they're not in each, imagine I've learned 1,000 affordances for this space. I should not think of them, of course, as 1,000 different unshared kind of meanings for this space, but instead I should model how these meanings relate to one another. And then that would allow to then think of like, how does this affect the acting agent, right? If it's that deeply aware of not just how things look, what they suggest about action, but then how those actions are related. So I can think of that as like a first order place where in our particular work, like the use of language could be enhanced or even help more.
So oh, go ahead.
Just briefly add to that, I think I think it's well said, Kristen. The thing that the word that I was hoping you'd use that you used once, but I think is more evocative of what you're saying is abstraction. So I think that we definitely need, and I think as a field, we're kind of recognizing that we need abstraction, and we're starting to look back towards the lessons of AI from like early '80s, but with modern tools and ways to learn those representations in new ways. To answer Jesse's question, whether or not language has, so I guess there's a question of where do the abstract symbols come from? And they could come bottom up from the perception and the physics, I think the way that you described, Kristen, or they could come top down from the language. And I think they're probably going to come from both directions. You need an abstraction bottom up so the robot has a complete representation that captures everything that it needs. You need it to come top down because you're going to want to be able to communicate it as well. So I don't think it's a either or, it's probably a combination of both. And if there's a role for language, I think it is as a source of additional abstract symbols that allow the robot to infer and plan more efficiently and communicate.
And one of the things I've kind of I'm still thinking through and kind of deciding what I feel about it, but I think it's an interesting consideration to say, like, we basically couldn't be nearly as intelligent as we are without language, right? And this can be kind of the caricature of this is the Worfian kind of viewpoint, right? That language influences how you think. And that's sort of like when you take any linguistics class, it's drummed into you that this is completely bad and completely wrong. But there's a different view, which is that the fact of language is what allows us to think, or at least allows us to think much more complex thoughts than we could without it. And I think maybe an interesting connection here is the technological hypothesis for the origins of language, which is that language essentially arose as our hominid ancestors were trying to kind of create tools and share, how did I construct this tool? How do you use this tool? And making more and more complex tools, that there was quite a large advantage that was conferred on those who could talk about these, instruct each other very concisely using language. And then you couple that with a lot of the reasoning that needed to be done about our sort of fellow people in our tribe and our society, and keeping track of relations and who did what for whom and these sorts of things. And it led to the need, or rather a selective advantage to those who could sort of make abstractions over their relationships, over their tool use and construction and so on, and then able to label those with language. Now, labels that are fuzzy and fluid, but still rigid enough that you could sort of transfer some reasonable reference between one mind to another. And so there's a question, I guess, of whether robots could actually engage in the kind of intelligent behaviors that people can do if they can't use language. Right? It might be that they're sort of stuck doing the things that we exactly precisely tell them to do, but they can't kind of do that more general intelligence kind of thing. So it's a thing that I'm thinking about. I don't know yet what the answer is, but curious what others think.
I do think that one thing that is worth remembering is that there are lots of animals that don't have any language that have remarkable motor skills, and motor skills that are well beyond where we are in robotics today. And I mean, some of it is, of course, like a hardware issue. We don't have robotic hardware that can do things that are as dexterous as what those animals can do. But in many ways, it is very much also a software problem. There's kind of a famous video of a PR1 robot being teleoperated to kind of clean an entire living room. And it's clear that it's like a living room that, kind of an average living room. And so it's clear that there is like significant hardware capabilities there, and we really just need the brains behind it. I do think that while we are like very much behind on kind of the robotics front, I think that the opportunity for language in my mind is figuring out how we can leverage language to make the problem easier, whether it be an abstraction, like Nick was talking about, or whether it could be trying to leverage the ease of supervising robots using language. It's very easy to provide lots of information via language, and maybe that can make it easier for us to provide supervision. But I think it's really important to focus on like actually trying to make things easier rather than making things harder. In fact, we actually got a reviewer comment on our paper on hierarchical RL with language as an abstraction, where the reviewer was talking about, well, why are you introducing language? Like the problem is hard enough. It's like, this is just going to make things harder. And one of the key things that we were trying to show in that paper is that it is possible to leverage language to make the problem, in this case of hierarchical RL, easier by using it as a kind of top-down abstraction.
Hi guys, I managed to turn my video on. Sort of somewhat following up from that direction. There's this really nice idea that's popping up in a few places about taking something like hindsight experience replay and then adding language to kind of relabel some episode with kind of language-based goals. And this was in your talk, Chelsea, as hindsight instruction replay, I think, but I've seen similar ideas. What do you think the limitations are for this if we want to get to really complicated language instructions, something maybe similar to the very difficult instructions in Alfred? Do you think this can be an idea that has legs, or will it have fundamental limitations?
I think that the idea is quite promising, and we saw significantly better performance when using kind of goal relabeling in the space of language compared to in the space of like a one-hot vector, for example. I think that the information that the structure and the abstraction that language gives you brings significant power. I think the challenge lies in making sure that the way that you especially the challenge with regard to scaling is making sure that you can leverage data that comes from people. And I think that this will, moving all of this towards natural language, I think will involve actually collecting data of people captioning different sequences, different video sequences, different interactions the robot had with the world, and then being able to learn, hopefully eventually some captioning model that produces kind of the instruction that corresponds to the video sequence that the robot saw.
I mean, also for the complex instructions or the commands, I think even the language understanding to follow commands or instructions, we can subdivide like simple problems and complex problems. So when I say simple problems, they are the problems that if you just listen to the language, you already know how to do your actions. So it's without vision. But there are complex problems even as a human. If you read maybe complex instructions to fix something, you grasp like a rough idea, but you don't know the detail. But if you look at the annotations or images or video, YouTube video on the same like how to, then you get a better understanding. So like when do we need both to follow or fully understand the intention of the instruction, I think.
I totally agree with Jean's point there. And this is where I think that treating the problem as intelligent question answering or embodied question answering, it oversimplifies the problem, where when you're forced to work with a real robot, you realize the extent to which even simple instructions are massively underspecified.
Mm-hmm.
Changing the oil in the car, no instruction manual would ever tell you to unscrew the cap off the oil container before pouring the thing in. How do we know to do that? That's got to come from somewhere. And so I think that as the instructions get more complex, the amount of information that is missing from the instructions increases exponentially. And so I think Jean's point is exactly right, is that we need to be able to do the simple tasks, and then we need to build a hierarchy. And I think that's to Chelsea's point as well, is that hierarchical models are crucial for filling in those gaps. I don't know if anybody remembers the movie from, like, I guess it's nearly 40 years ago, Short Circuit, with the robot that gets hit by the bolt of lightning and then like becomes, I guess, sentient, etc. And like, as it's reading and it's learning to do things, there's moments of hilarity where like it skipped crucial steps that a person would never skip that lead to failures as it tries to understand the world. And that is what's one of the things that's making natural language instructions really, really hard, especially for complex tasks.
And I would say it's also related to how we actually understand sentences and multi-sentence utterances, where we fill in all these gaps just effortlessly in language because we know about how the world works. We build representations of situations and objects, and then it's this constant mutual constraint satisfaction.
Along those lines, there's this fun game that you can play where you blindfold one person and the other person has to give instructions to that person, and it kind of reveals how much common understanding you typically use by shared perception that you now have to figure out how to communicate when one person doesn't have perception. And our robots are lacking that kind of perceptual, or maybe lacking some of that shared kind of understanding that we often assume when we're communicating with language.
That also touches on an important problem in language, which is when you have multiple people or agents in a situation, they need to do pragmatic reasoning about each other's intentions, actions, goals, and so on. And that's something I think we're just been able to scratch at so far, especially in these kinds of environments.
Okay, I'm going to shift gears a bit. So there's a spectrum of learning. So on one side, we have learning from interaction, purely learning from interaction. And on the other side, we have supervised learning, and we can learn from get annotations from crowdsourcing and learn those. So and so far we have seen like great performance using supervision. So what's the right way to go? Like, is it is learning from interaction the way to go, or is it, or do we need like some hybrid approach, or what's the what should be the balance?
Well, I think it depends on what your ultimate objective is. So if your objective is to get a robot to exist in, say, a factory floor, then I think that supervised learning is probably totally fine. But if your goal is to actually have, like, I guess the moral equivalent of AGI, but as in a robot, where it's able to explore the world and to build its own representations and recognize the fact that the world is partially observable and non-stationary. So representations you start off with at the beginning of its life need to change fundamentally over time, then it's pretty clear that supervised learning would at best give you a prior, and then interaction learning is what's going to be needed over time. The world is non-stationary, partially observable. The data is not IID. I mean, these are all things that are crucial for a robot that don't match the assumptions of supervised learning. So I think it depends on what you want.
I think part of the challenge with interactive, again, is if you're engaging in collaborative, complex behaviors and languages involved, it's hard to get to basically source the human-created language for that's in context. And so again, I think one of the hopefully promising things we can do, and maybe like the fact that we're doing all this, doing panels this way rather than in person, is a pointer toward the potential ability to use things like games and environments to build interactive ways for bots and people to talk, learn, and interact. I like some of the work that Yoav Artzi has been doing around building games that are collaborative between a human and an agent. So he has the cereal bar game where the agent has certain abilities that the human player doesn't have. So they're trying to solve basically the game of set in a little 3D environment. It's a game-like environment, not photorealistic, but essentially the person can give instructions to the AI agent, and the AI agent can move like 2 or 3 times as far as the human agent can in terms of like going to cards and selecting cards and then solving sets basically. And I think it's really interesting to have these sort of situations where you have an asymmetry between what the AI agent and what the human sort of avatar can do in these environments, so that language really matters. And you have to kind of, the agent really needs to understand things better to get that right. And it is interactive in that case, right? It's not just train on only, or work only with demonstrations.
I also don't think that these two paradigms are necessarily mutually exclusive. I think that you could collect some interaction data, store it offline, and then collect some annotations on top of that data. And that may look like something a little bit more of a hybrid between these two. And I think that we should, in some way, I do think that robotics should leverage some of the kind of successes or some of the lessons learned by learning from very large scalable data sets that has been very, very successful in computer vision and in natural language, and maybe storing interaction data and annotating it might be a step towards that. The other lesson potentially to be learned from language is to figure out how to get the most supervision out of the data that you have, whether it be a self-supervised signal or something else.
Yeah, I think we can definitely look for hybrids to these things, and maybe one form of hybrid was trying to learn by watching people, but not watching them in the sense of recording the states and actions they took, such that we would try to translate them as supervision to the robot, but instead looking to how people are doing things to understand, I guess, the higher order bits. So something about, like in our work, this means things like how do objects get used, where are they touched, maybe how are they touched, but in where are they touched to do different actions, or when we look at a physical space like a 3D environment, where are the regions, like the portions of this environment where activity is very probable or possible. So these are examples from my talk in this workshop, but I think it's a taste of this general direction we can keep pursuing, which is somewhere in between of exactly, hand-holding, supervising state action pairs to an agent versus, letting it just go off in the wild and do it on its own. And this is kind of in between, like, let us see experts do things, but in their own habitat, meaning, people not in a lab environment, people hopefully, just wearing a camera or doing something in the wild, so that we can translate from the perceptual stream favored places to be, objects to have, things to do that's a little bit, it's a step removed from direct supervision, but nonetheless would allow to shape kind of the interaction that the agent would choose to do on its own.
I also like the idea of a hybrid approach here. So maybe we can provide some supervision, but for robots, if we can have a very nice simulator where the robots can practice what the supervision is taught the robot. So it's kind of combination of supervised and unsupervised.
One of the things that I think would be really, really cool, I don't know yet how to bring this about, but would basically be to have a world-spanning augmented reality game. And sorry, I don't really work much with robotics, so I think robotics is awesome, but let me kind of go into the more like just simulated world thing. But one of the things that our team is focused on primarily have been sort of photorealistic environments that are grounded in the material world, rather than say like, a video type game setting. And one of the things I think would be so cool is to have something along the lines of Pokemon Go crossed with Minecraft, where you would have people out in the real world trying to solve tasks, kind of do in-game activities that would get them points and things like that. And there would be agents that would be sort of moving around, living in this environment and able to help them out and accomplish your tasks. So say like you needed to collect some wood resources to build some virtual 3D object that actually is located at a particular geolocation. And the thing that I think would be so cool is if the agents basically got their compute resources based on whether they were able to be useful in the environment. So this goes back to the original question that Roosevelt was asking, which is would interactivity be the right thing? And for me, that would absolutely be like the most exciting way for this to happen, because I think the human language would be more on point. It wouldn't be the kind of crowdsourced stuff that tends to be a bit like, okay, I'm being paid to to build these instructions for you and so on. No, I actually have goals in this setting. It's a dynamic setting, so I might actually do more stuttering. I might like back up. I might go, wait a second, let's do this instead. And then the agents would have a lot more stake in it, because they would basically live or die based on whether they could succeed in that. It wouldn't just be, oh, I got a reward or I didn't get a reward. It would be, I cease to exist. And then you throw that in with some evolutionary type thinking, evolutionary algorithms and whatnot, and it might be really exciting. Of course, there's a lot of infrastructure to build that, but I don't think it's completely inconceivable that this would be possible.
Thanks, guys. So we have a question from the audience. So I'd like to recognize Shordro to ask a question.
Hi, everyone. So for those who don't know me, I'm a graduate student at the University of Michigan, working in vision and language and working with robots, real robots. And I think, as has been pointed out by everyone here, real robots are hard, and they incur a lot of problems when you're actually trying to work with language data. So my question is more like introspective. We talked a lot about what we need to do as a community to move forward. But I was wondering, especially from the panelists who've been in this field for a long time, are there any advancements that the field has made in recent years that are really worth like looking back at and saying, wow, we've done a good job at kind of this task that I thought would be much, much more complicated, but we've actually solved this problem. For example, like obvious things, for example, are maybe like embeddings in like language embeddings and visual embeddings. We've become much better at like processing or perception. But are there any other non-obvious advancements that maybe you look back and marvel at that we've come a long way?
Is the question specifically about natural language vision and language, or is it just more general about sort of intelligence?
I would say it's two-part. It's starting with vision language because that's the main subject of this talk. But if you have thoughts on like general intelligence that you would also like to describe. I would love to hear those thoughts as well.
Well, I guess one easy one is like in robotics, I guess the ability to navigate without GPS and to build maps of the environment. Not just the SLAM problem, but the more general, like, environmental reconstruction. That works way better than it did 10 or 15 years ago. It's almost a commodity technology for certain kinds of environments. So that's one example, I think.
Also, I mean, everyone knows that there was a huge progress in computer vision, but the applied field in robotics, when we used computer vision just a few years ago, it just didn't work good enough to support the robotics tasks. But these days, it's like getting towards a really usable level, so that I think that was a really like game changer in robotics. And also the availability of these like new data sets with the newer sensors like Matterport, that's really encouraging people to create larger data sets and really nice, well labeled like portions. So I don't know if that counts as a progress.
I would say from the language side, it's amazing that sort of the representations produced from computer vision and language actually can kind of talk to each other. And so each of these, you mentioned each of these individually, but the fact that they are sort of so compatible, at least at a low level, is really exciting. And so I think now we have to think about what are the abstractions we can build on these so that we can generalize better on the language side, represent better on the computer vision side, and continue to have those interactions between these two modalities, and say like action arise more fluidly. It's a really exciting time and place to be, because we're really set to make more progress. And the one thing I would sort of add to that is I think natural language processing in the like early 2000s was, I don't want to say plagued, but kind of plagued by feature engineering. And we had some tools like logistic regression and support vector machines and various interesting ideas, but a lot of papers are kind of like, all right, so there's this classification task that I want to do, and so here are the features that I added, and here's my feature ablations, and they had these long boring tables. I have some papers that include these long boring tables of features, and we kind of like all of these things, not just deep learning, but then into the models that we have at BERT and whatnot, are kind of helping us clear that rubble away and focus on higher level concerns. But now you're starting to see, I think, more of the kind of equivalent of feature engineering, which is like data augmentation engineering, tweaks to architecture engineering and things like that. And that starts to smell very boring. And so I think we have to kind of continually be reinvigorated from other ideas. And I would even encourage people to look back 30, 40 years ago in the literature on cognitive science, linguistics, whatever, to maybe find more inspiration for ideas beyond just nibbling around the edges.
I think computer vision is going through much the same problem, and I think robotics is also sort of starting that. So what tends to happen is that people find a way to sort of tackle the problems, and they find a data set. So I think in those papers you mentioned, Jason, you probably also saw a lot of long boring tables evaluated on the Penn tree bank. And then everybody's like, wait, this is a terrible idea. We got to stop accepting papers where it's just like 1% better performance on Penn tree bank. So computer vision is, so ImageNet, is sort of driven that. And so I think, and the moral equivalent of long boring tables are the giant architecture diagrams of here's my network. Perhaps you would like it.
My novel network. My novel network.
Yeah, right.
In the paper submissions you read, they're always their novel network. It's like I changed this little thing.
But I think that's starting to go away as people realize, like, we massively overfit to the data sets, and it's like the problem is fundamentally somewhere else. And I think you're right, looking back 30, 40 years is good. And robotics is currently, I think, not quite, but basically about to be in that point where we're massively overfitting to the kitty data set. And so I think that, right now it's very hard to get a paper published in sort of computer vision applied to robotics where you didn't evaluate on kitty. And that's going to probably last another year or two, and then we'll stop and realize the problem is somewhere else. Every field, I think, goes through this, and then everybody's like, wait, this is a bad idea. We should stop overfitting to these data sets. We should stop just trying to get incremental improvement by tweaking our current way of thinking about the problem, and take a higher level. I completely agree with what you said.
Robotic manipulation, I don't think we have this problem because we don't have really any benchmarks, so that's
Right.
maybe good, but we have plenty of other problems. I think that retrospectively, I think that some of the things that have impressed me in manipulation are more along the lines of what we've been able to get robots to learn through reinforcement learning. So we've seen a 5-finger hand be able to like rotate 2 balls in its hand, 2 bounding balls, which I found pretty impressive through model-based RL. I had a paper back in 2016 that I'm still retroactively impressed by, where we got a robot to use a spatula to lift an object into a bowl, where it had to figure out how to get the spatula underneath the object. But in both of those situations, the generalization capabilities of the robots are really terrible. It was trained with that one spatula, with that one object in that one environment. And if you give it a different spatula, put a different tablecloth down or whatever, it won't be able to generalize. And so a lot of the work that I've been doing more recently has been trying to focus on how we can move towards systems that can generalize to different objects, to different environments, and so forth. As a result, the skills have looked a lot less impressive if you're looking at a very superficial level, because we're doing simpler skills, but emphasizing more the generalization side of things. And I hope we can get back to the point where we're doing very dexterous and challenging tasks, but also considering generalization.
Does that sometimes make it harder for a paper to get accepted, or like reviewers are like, wait, you didn't get this top number because you're actually trying to solve a broader problem? Or
in some ways, yes. I think that you definitely need to look carefully into the experiments and think carefully about what they're doing when reviewing a robotics paper. Also, there's a lot more emphasis on really laying out all the details of your experiments, because each experiment is different. At the same time, I think that there's kind of an accepted standard in manipulation that you're not solving a benchmark. You are trying to solve a problem, some research question, whatever, that you lay out very clearly. And perhaps that's maybe something that other fields could learn from.
Mm-hmm.
Thanks, guys. And thanks for the question, Shorjo. We have a couple minutes left. I'm going to ask a question that would probably push us over time, but if people need to drop off, I'll quickly note that our plan is to transition from the panel into the social hour after this. So I'll put a link in the Zoom chat to a gather.town instance, and all of the attendees are invited to congregate there in our virtual poster room from yesterday. If any panelists are still available for the next couple minutes after the panel, it would be awesome to see you there as well. But a sort of closing question that I have, and I think a couple of questions have touched on this already, is a discussion that in particular Jonathan Bisk and I have a lot, and he's not here today, but is one of the main organizers of the workshop. While trying to, as primarily language people, push into both vision and robotics, a question we come to time and time again, especially in the design of data sets, is what level of abstraction is appropriate for what we want to do. And from the robotics perspective, I think often the level of abstraction we want is quite low level. You actually need to be controlling a motor, controlling a gripper, doing something in the real world. And from the natural language perspective, by contrast, the notion of having even a semantic formalism is a little bit difficult, because there are words like open that are not easily represented as sort of an API call, right? A roboticist might think, okay, open the door is challenging because I have to control a gripper and there's lots of different doorknobs. And an NLP person will say, well, open is hard because the way that I open a door looks nothing like the way that I open a bottle. And so I wonder, sort of from the panelists' perspective, is there sort of a place we, as these three sort of distinct communities, can agree on for a layer of abstraction that makes sense? Do we always have to go down to motor level control? Is there a middle ground for representing sort of verb actions and noun abstractions that can make sense for both robotic planning and manipulation, and going all the way up to sort of the analogies and ambiguities that Jason thinks about?
I guess my answer would be there isn't, even in none of those three areas is there one abstraction that I think is the right level of abstraction, and that makes, and especially for the combination of those three. And I think it's important that the abstractions be hierarchical. I think Gene has heard me say many times is that, we have this problem of like, connecting the different levels of abstractions in robots. And usually what ends up happening is that some engineer or grad student writes the higher level abstraction, and like there's always like some piece of C or Python that connects the lower level to the higher level, and that's the thing that always breaks. And so the robot does something dumb, and so you're like, why did it do that? It's like, oh, I forgot an edge case, or I forgot this part of the abstraction. And so if the thing we don't have is a way to actually learn the hierarchy of the abstraction, so that when new data comes in that doesn't fit, we can adapt. So I'd say two things. One is there isn't one. There's got to be a hierarchy of abstractions, and we need to figure out what the objective function is that actually allows us to learn that hierarchy in some way.
And I don't know if my answer is relevant to your question, but this is more of a wish list from the robotics to the language people. So the data sets, so the way usually it's organized is the perception was done in a more or less perfect way, so that labels are available. But if the language people can assume that maybe there is no vision, but based on this description, can you guys provide more information to actually see better? So for instance, if it's finding a cup, then without relying on vision to detect the cup so that you can find it, maybe provide the properties or something that we can learn from the language side to describe the cup, like what to look for the vision system. So that's something that I wanted to maybe convey. Yeah.
That definitely is part of what I'm hoping we can get at by looking at this this sort of layer in between low level and like abstract language, where you can think about the abstract language representations as being, like your BERT embeddings and even like good old Word2Vec and things like that, and these low level action and spatial representations. And there's this kind of thing in the middle that I think we need to sort out that has to it probably has some dimensions that are common across all of us because of, basically our evolutionary past all the way back 200 million years, whatever, of understanding that there are things like color and shape and size, weight, and things like that. But each of these corresponds to a convex sort of space that represents a sort of semantic dimension. And this is, again, Peter Yardenfor's ideas. And that there are many of these different dimensions. They have correlations among those dimensions, and the language sort of attaches to them in certain ways. And the thing, though, is that we can't sort of like predefine exactly what these shapes look like because they're different for different people, right? For example, I'm actually colorblind, and so I don't see the color space the same way other people do, and yet I still manage to figure out most of the cases of like reds and blues and greens and so on. And so to Nicholas's point, it's like there's not like some API that we can code up, I don't think, but we need to figure out what are the kind of architectural structures so that this process can be sort of learned in some way from some data, possibly even pre-trained and shared, and then we kind of move on from there.
Yeah, I totally agree with that sentiment and what's been said. I think, it must certainly need some kind of hierarchy in these granularities, and hard challenges are ahead or are with us in terms of how to not just have that hierarchy, but then seamlessly, fluidly acquire new things that we learn in the right parts of this hierarchy. I guess one consideration for us, practically speaking, today is, are we still, we hope it's the case that nonetheless work can go on at these different levels, even independently, because there's big chunks to chew on, even if you work at, with this granularity or this one, and people are, so being conscious of the ultimate goal, I guess the hope is to be that this kind of work done independently can eventually come together. And so all that just emphasizes that probably a good research direction on its own is thinking about the integration and the hierarchy and the meta issues that would span all the great work that's happening at different levels of granularity now.
Yeah, I agree that integration is a challenge, and I think I'd love to see work on kind of all different aspects of this, where some works are focusing on kind of the lowest level abstractions, some works are focusing on the higher level abstractions, and other works are looking at how you actually integrate those kinds of integrate and create an interface between higher and lower levels of abstraction. The other thing that I would say is I do think that it's worth, when you are isolating a problem, it is worth trying to be upfront about the limitations of that and the fact that you are assuming that you have, for example, like a policy that knows how to open a door, for example. And one of the things that I really like to do is to every once in a while do actually go back to real robots and see what the kind of the big challenges are there. And I think that that really keeps you in touch with what the true limitations are when trying to tackle some of these problems. And I'd love to see more of that across the board, where more people are every once in a while doing kind of experiments on real robots and understanding where the gap is.
Thank you for those insights. So I know that we're past the time that I told the panelists that I would like for them to be available. So if you have other places to be, please feel free to jump off. The idea of the GatherTown instance, by contrast, is instead of having this sort of monolithic, only one person can realistically speak at a time, there's a sort of geometric embedding to where people can hang out, so they can go like stand near a speaker and talk just to that speaker or be in a different group. So I welcome everybody to move over there. If it works really terribly or there's bad connectivity issues, we'll come back over here. So I'll leave this room open as well. But thanks to our panelists for being here today and for this discussion. It was really exciting for me. And I hope to see you guys in the GatherTown now. Thank you.
Thank you.